Yeah, very welcome today's digital class. Today I am going to take the class of binary adder. I am Pampa Nandi. So my topic is today's topic is the binary adder. Binary adder, and here you can see the topic I am covering here: half adder, full adder design using half adder, and the binary parallel adder. So first, let me describe what is a full adder or adder circuit. This is a combinational logic circuit. In digital, there are two kinds of digital circuit, that is combinational digital logic circuit and sequential digital logic circuit. In case of combinational logic circuit, there is the characteristic of this combinational logic circuit is its output is only depending on present input only. There is no feedback path. So, in case our adder is belongs to that category. Now, that is first why we are saying that is why it is required, because through the computer we are performing various kind of arithmetic operation, and the basic arithmetic operation is the addition. Now, when we are doing the binary operation, so it is doing the bit by bit operation. So first, when we are checking, you can see here also that we are I mean that 2-bit addition can produce two kinds of results: 0 plus 0 single digit output, 0 plus 1 single digit output. When it's come to the addition of 1 plus 1, then it's producing 2 bits, that is 1 and 0, which is equivalent to 2 in decimal. Now, then here when the 2 bits are coming, so the lower significant bit from the output we will call the say sum, and the higher significant bit we call as carry. Now, let us go in detail. So first, which is the very basic building block of the adder circuit, binary adder circuit, is the half adder. Half adder is a digital logic circuit. This is a combinational logic circuit, as I mentioned, which can add 2 bits simultaneously. So here is the I have made that suppose it has two input x and y, and it can produce the outputs like carry and sum. As you can see from the truth table, that is 0 0, it is producing carry 0 sum 0, and when 1 plus 1, that is addition, then it is producing higher order bit, carry equals to 1 and sum equals to 0. Now the procedure at how we can design this circuit. Now that from the output and the input combination, we will make the simplification of the logical function. For this, though it is a very elementary, we directly can make it, but that is we need to show the practical, I mean that the procedure. So that's why I kept it in two Carnot maps, one for sum and one for carry. Here you can see the sum is producing x bar y and xy bar, that is the only that the expressing the that is the XOR gate, and here the carry, when 1 1 is there, then the carry is producing XY. Here you can see the circuit diagram accordingly. Now how you can see? Now that is x bar y, to make this one x input we are placing through NOT gate, so it's become x bar, and this is y, this is AND gate, it is producing output x bar y. Then again y bar, and with x it is producing a y bar x. Then addition using 2 OR gate, it is producing the sum, that is x bar y xy bar. And here for this one, the carry, we are only simply taking the input from x and y and putting through this one value through the AND gate, it is producing the value of carry. Now come to the point that, as I mentioned, that in the second expression, that is, it is the nothing but the expression of XOR gate. So directly we are putting the XY in this XOR gate. So we get directly sum, and through this AND gate we are getting the carry. Now, if we want to make adder which can not only adding 2 bits, so if that the carry is generated, that should be adding with the higher order bit. So higher order bits. Now for this reason we are designing another circuit that is called full adder. So full adder, again, what is full adder? Full adder is a digital combinational logic circuit which can add 3 bits simultaneously. Here I have mentioned the input bits are x, y, z as the variables. Actually, in case of when we are designing in practical case, then we are, in case of z, we are using the carry from the previous bit addition. So here again the same thing, it has 2 output, that was the 3 inputs x, y, z, and then the 2 output sum and carry. Here you can see, and one interesting thing, that is, it is how it is doing the addition, that is x plus y plus z. So again the binary addition is done, and you can see here the most interesting case here, when 3 inputs are 1, 1, 1, then it is producing sum equals to 1, carry equals to 1. Again, now we are going to design the full adder circuit. So, full adder circuit, how we are doing? Now, first we simplify the truth table using for sum and carry using Carnot map. Now, here you can see that is the Carnot map for the sum, and here this is the Carnot map for carry. Now, as you can see that the sum, when you are there is no group formation of simplification, so directly the value from this Carnot map we are getting sum value is x bar y bar z, then x bar y z, like this, which is after simplification it's become what? X XOR y and XOR z. In that way, carry is equals to, carry becomes xy plus yz plus zx. You know that how to do the simplification. There is the group, making the group through this Carnot map, and after that the simplified version you will get the carry. Now here again we are showing in two way the making of this, one with the basic gates, another one is the using the derived gate. Now first one is basic gate, that is x, y, z, my 3 input, I put this in 3 input XOR gate, so it's become x bar sum, we are getting the value of sum x XOR y and then XOR z. Then again to making this one xy plus xy plus yz plus zx, so every 2 input like xy we are taking for gate, one AND gate, for yz another AND gate, for zx another AND gate, and their output is that accumulated through the another gate, that is OR gate, and producing the carry. Now that is very important and interesting thing, that is this type of circuit is getting more number of gates. So now we are planning to make, that is using 2 half adder, that we can make then one full adder. You can see here that I have using 2 half adder, here first block of 1 half adder, second block of 1 adder, and with one this one another OR gate, we can get this one. For this we need to do some extra work, that is for sum it is not a problem. For carry, to generate the carry, we need to simplify this one according to the half adder format, and we are getting after simplification using 2 fit for the system for half adder, that carry expression is now changed x plus y x XOR y, that is with multiplied by z plus xy, and you are getting the result for full adder using two half adder, which is the most compact form. And the last one is, this is the last but the not least, that is binary parallel adder. Now till now we are talking about that is how we are adding 1 bit to 2 bit or 3 bit. But when we are taking two digital numbers or binary numbers, then it is not is having it is not having only 2 bit or 3 bit, two numbers. So how we are adding two numbers? So parallelly, what we can do, that is we are using binary parallel adder. Suppose if we want to add n bit, so we are taking n number of full adders. Suppose in case of here the example, we want to add two 4-bit binary number, so that's why we are taking 4 full adder. Now that is A1 B1, A2 B2, A3 B3, A4 B4. So one number is A, which is composed of A1, A2, A1, A2, A3, A4, and another number is B, which was composed of B1, B2, B3, B4. And here for this previous first, any input carry is there, and every full adder is producing sum, and the carry from the first full adder is feeding to the carry for the second, then second to the third, to the fourth, and the last one is the final carry. In that way, we can add any number of n bit addition. So here is the something we are showing like this way, and here I will conclude, that is with the some, that is uses of full adder. This is the building block of any arithmetic operation, building block of any ALU. And if you know that when we are performing the subtraction, then also we are using the addition process, so which we will show you in the next class. Till then, thank you.